Hi, everybody. Welcome to the week of April 13th through this Friday, April 17th. Before I get started in our physical science lesson for today, I'd just like to walk you through some updates that we have going on. So, I haven't really released how you're going to be graded during this time, so here's a little bit more information about what that's going to look like. If you've noticed on Infinite Campus, I've taken out the final exam category and I've replaced it to be now titled Home Learning. So the reason we're doing this is there's still going to be a final exam category, or there's going to be a final exam lesson or activity that I'll introduce later in the semester. But for now, we're going to allocate that 12% in your grade to everything we're doing now in home learning. It makes it easier for you and me to know and see what exactly you've been earning during this online portion of this class. For the next unit on bonding, which we started last week, here's kind of a breakup of how the points are going to work for those things. So you did the Mickey Mouse molecule activity last week. If you completed that, you got 15 points. And then this week, you're going to be doing a periodic trends activity as well as a self-quiz. 25 points for the periodic trend, 15 for the self-quiz. Then after that, the following week, you'll have a few more activities going through the rest of our packet, each worth 15 points. And this totals to 100 points for this entire unit. I will give you an update when we start our next unit on what those points and what that grading is going to look like. I want to let you guys know you're all doing a really awesome job. I'm so proud to be working with all of you. I appreciate that you're checking in with me, writing me emails, asking amazing questions. I wanted to let you know a little bit about our Boulder High policy right now and what's expected of your activity during this time. So, students are still expected to be active participants in all of their classes. If you would like to maintain your grade or raise it to be higher, you need to be actively engaged and responsive in what we're doing. You all have been doing an amazing job at that. I do want to let you know, as we're moving forward in the rest of the semester, if you have not been actively engaged over multiple weeks, then your grade is at risk of being lowered for this class. It's a very vague outline, but I just want you to know that if you keep up the good work, you shouldn't have to worry too much about your grade in physical science. Another thing is if you're having any trouble logging in, you can't really find assignments, you're just feeling generally stressed or overwhelmed by everything that's new happening in society right now, I want you to know that it's okay. You can stay calm and that you are not by any means alone in this situation. So, as always, please communicate with me if you're in need of any extra support for anything for this class or at Boulder High School. I know it's been difficult and different that we're not actually at school physically together, but I just don't want you to forget that as your teacher, I'm always here to help you, and you can email me or talk to me anytime. Here's some more instructions on how you're using Schoology to know what you're doing every single week. So all of you have done a really good job of logging in and doing the attendance quizzes. That's essential for me legally reporting your attendance and saying whether or not you actually checked in with me on the day you were supposed to in the schedule. Once you do the attendance quiz and you're like, what do I do now? Well, when you go to Schoology, you can go on the left-hand side under the cat that says physical science, and you should click on updates. Once you're updates, you'll see a whole screen of different posts that I've posted over the past couple weeks. You'll want to click on the post that says week of and whatever dates they are right now. So for this week, you click week of 4/13 through 4/17. I'll have a little bit of text, and you'll want to see the whole message by clicking show more. Once you scroll down into that post, you'll see a purple calendar that outlines what you should complete that day. There's links to videos, there's instructions, and there's due dates and how to submit things. Once you've done that, and if you still have questions on what you're supposed to be doing, I would love to help you with your questions, but I'd really love if you could start by looking here and looking for the information yourself. I am available for Google Hangouts Meets every single time we meet for class. So if you're scheduled to come to class from noon to 1, I'm here from noon to 1 on the Google Meets link. Sometimes you'll see that I've been requiring that you actually check in with me there. Sometimes it's just a great place to log in and know that you can actually see me face to face and ask a question. Thank you to those of you that are utilizing this service. If you haven't, please come check in. I would really love to help you and see you over video. You can click the same exact link we've been using during this whole time. It's right there on Schoology. It says Ducey office hours, and I've posted it multiple times in the updates. If you're not comfortable with that, you're also more than welcome to email me at any time. This schedule this week is a little bit different. You have a 4-day weekend coming up. So there's no school this upcoming Friday, and there won't be school the following Monday on the 20th. There's not going to be any official school activities, but I'm going to keep all of the due dates open for the activity this week until Friday evening. I'm doing that so that if you get busy with your schoolwork Monday through Thursday, you don't have to do school on Friday, but if you feel like you need a little bit more time, please utilize it. Everything, like normal, will close at the end of the day on Friday on Schoology, and that's when you need to turn in all your assignments for it to be on time and for you to get credit for it. Okay, so that kind of leads us to how are we starting this next unit? Last week we did notes on a cation and an anion in the Lewis dot structure, and you did a Mickey Mouse molecule activity. I'm going to review that here in a second. I want to let you know that this week we're going to be doing a trending activity today, and there's going to be a short self-quiz at the end of the lesson on Thursday. So let's review this Mickey Mouse activity first by looking at how you would have built your molecule. I'm going to let Mr. Sullivan take it away.
Oxygen's electrons are being shared in order to complete hydrogen's first energy level. Now hydrogen's happy. Over here, now hydrogen's happy. But oxygen's happy as well. 1, 2, 3, 4, 5, 6, 7, 8. That's kind of how it works as far as what a covalent bond looks like. Those are sharing electrons. These are sharing electrons.
So after you made that model, you should have answered a few questions. You see that protons and neutrons are available in the nucleus, while electrons are always orbiting around the nucleus. And when we're filling our energy shells, there's going to be 2 electrons in the first energy level and 8 electrons in the second. So how do the hydrogens and oxygens fill their energy levels? Well, hydrogen and oxygen fill them by forming covalent bonds, and that's when they share electrons. And when they share those electrons and they make their outermost energy level full, it makes them really happy. Water is a polar molecule because you can see that the hydrogens are located near to one end and the oxygens are on the other. This makes one side of the water molecule positive and another side negative. You can kind of think of this polar like the north and south pole. You have opposite ends, just like a water molecule. Opposite, instead of north and south though, we have positive and negative. And what's the shape of a water molecule? Well, it looks like Mickey Mouse because it's polar. It's bent with our hydrogen protons on one side and most of our oxygen's negative electrons on the other. So let's look at our objective for today. At the end of today's lesson, you should be able to describe the general variations in physical properties across a row or column of the periodic table. So we're going to continue to review bonding and look at trending of the periodic table. The activity that I'm going to assign to you today will be due by the end of the day on this upcoming Friday. So when you're taking out your materials today in your home learning packet, you're going to start with the one that's number 3, it's titled Periodic Trends Activity, and then later in the lesson we're going to work through the rest of the pages that also say Periodic Trends Activity. So we're going to start with a question of the day. This is where you should pause the video, take a moment to exercise your brain, get it ready for science, as you're starting to think about some of the information that we learned last week. Okay, welcome back. Let's look at this matching section. So we're looking at the difference between an ionic and a covalent bond. An ionic bond is a bond that involves losing or gaining electrons because they're taken, and a covalent bond is B, a bond that involves sharing those electrons. When you're looking at the two pictures below and you have to match one to the other, an example of an ionic bond is salt, sodium and chlorine coming together, where chlorine takes an electron away from sodium. And an example of a covalent bond is here in water, where hydrogen and oxygen both share their electrons. Today we're going to be looking at trending on the periodic table. Here's some key questions that I would like you to write down that we're going to be answering in our activity today. 1. Are all atoms the same size? 2. Does the size of an atom have an effect on bonding? And 3. Are there specific properties that make some ionic bonds and some bonds covalent? Our background information today is two new key terms. The first is ionization energy. This energy is the minimum amount of energy that would be required when we want to remove an electron from an atom or a molecule. This is usually in the gaseous state of a molecule, and this is when you're thinking about when we're taking electrons away from one atom and bringing it to another to form an ionic bond. The other new term that we're learning and talking about today is the atomic radius. This tells us the size of the atoms, and it's typically talking about the distance from the center of the nucleus to the outermost boundary of the atom, so usually to the furthest energy level where all of your valence electrons are, and that's the boundary of your surrounding cloud of electrons. So let's look a little bit more closely at what that means.
How do we know if it's which ones share and which ones are ionic? Truth of the matter is, this is all that size. So if they're different in sizes, they're gonna be ionically bonded. One's gonna take from the other. If they're very similar in size, then they're gonna share. Let's say you got this little feisty guy here, little karate guy. Okay, he's little but he's feisty. He's high energy. Then you've got Cartman from South Park, who is, he's got his cheesy poofs here, and he's not as feisty as this guy. Even though Cartman is bigger, Cartman's probably going to lose in a battle against this little guy. So in reality, chlorine always steals from sodium chloride. Okay, big guy is going to get his cheesy poof or his electron taken from this guy. And that's sort of kind of how we're going to talk about this. So, but if they're the same size, they're going to have the same feistiness, and they're just going to end up sharing electrons. No one's going to be able to take from the other. So when you look at the periodic table, if you have two things going against each other, if you will, that are different in sizes, they're going to ionically bond. If you have something that is similar in size, they're going to covalently bond. So let's look at hydrogen and oxygen. Okay, they're pretty similar in size. They're going to covalently bond, H2O, the Mickey Mouse molecule that you just made. But if they are much different in size, like I said, sodium chloride, you can say, oh, they're gonna ionically bond. One's going to be able to take from the other.
When you're looking at trends of atomic radius, as you move downwards on the periodic table, the atomic radius is going to increase because you're adding more and more shells. The more shells there are, the further away the edge is from the outermost area to the nucleus. As we're moving to the right on the table, atomic radius decreases. When we're adding more protons, this has to do on a chemical level, talking about the strong nuclear force. The more protons there are, the tighter it hugs in those electrons closer to the nucleus, and the smaller the atom is. This means that atomic radius increases down and to the left on the periodic table. When we're looking at ionization energy, which is the energy that's required to move an electron from the atom, We're always going to be talking about removing a valence electron. It's a lot easier to grab an electron from the outermost layer than to try and dig somewhere in the middle. The farther an electron is from the nucleus, much easier it is to pull it away. This means that on the periodic table, ionization energy is opposite to atomic radius. The energy increases up and to the right on the periodic table.
Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium.
We're done with the note-taking part of our lecture, and the next section I'm going to be utilizing to explain your activity for today. You're going to need these next 5 pages in your home learning packet for the activity. Let's start by taking a moment to read through the instructions. So the description says that the table below shows information for select elements in periods 1 through 6. In each square, you will find the atomic number, the atomic symbol, and atomic radius, how wide the atom is, and the ionization energy, how much energy is required to remove one electron. The order for this information is shown below. We have an example with strontium. So here, you can see in this example for strontium, we start with the atomic number at the top, then we list the symbol, then they list the atomic radius and the ionization energy. I want to take a second to pause and talk about units. They don't really have any units listed with any of these numbers. I want to let you know that atomic radius is typically really, really small and is expressed in nanometers, which means it's in scientific notation times 10 to the negative 9 meters. For ionization energy, it's typically described in kilojoules per mole. Now, what should sound familiar to you there is that joule is a unit of energy, and we're going to actually learn about the mole in our next unit. But just know that for ionization energy, the unit is in energy. Part 1 of this activity involves graphing. So you have this periodic trends activity out in front of you, and down below here, there's a bunch of directions that I'm going to walk you through. We're going to create 4 graphs, 1, 2, flip over, 3, and 4. So let's start with the first one. This one says that for elements 3 through 20, we're going to create a half-page graph of atomic number on the x-axis versus atomic radius on the y-axis. So this means we only need to look at elements 3 through 20 to create this graph. When we're looking at our numbers, if we're following the key we have here, let's start with lithium. We're going to graph our atomic number on the x-axis versus our atomic radius, which is the third line item down on the y-axis. So if I'm doing lithium, my first data point I'm going to start out with is I'm going to go to my atomic number is 3. So I'm going to move my pen over to number 3 on the x-axis. My atomic radius is 1.23. So I'm going to move my pen up until I hit the line of 1.2. I'm going to have to estimate the 3 there. So I'm going to estimate a data point there for about 1.23. Let's also do beryllium. We have an atomic number of 4, which puts me over here, and an atomic radius of 0.89. So I start at 4. Now 0.89 is going to put me here at about 0.8. It's almost 0.9, which puts me here. So you're going to continue that for the rest of the data points until you get to calcium atomic number 20. Don't forget, as you're going through and following the instructions for your graph, our next step is to connect your data points with a straight line. Don't forget to be using a straight edge when you do this. And next, we should also draw a vertical dotted line separating different periods on your graph. For example, you should have a dotted line separating neon, atomic number 10, in period 2 from sodium, which is in period 3. Let's move on to the second one. This time, you're still plotting the atomic number versus the atomic radius, but you're going to have to create a key of group 1 versus group 2. You can do this using different symbols. You could do this using different colors. I'm going to use colors. So I'm going to have green be my group number 1, and I'm going to have this kind of lightish purple be group 2. To remind myself while I'm going through on my graph, I'm going to look at my groups over here on my periodic table. Group 1 is right here, and that's what I'm graphing, versus group 2 right here. So I'm going to start with my line for group 1, and then I'll move through to group 2. What you'll notice that's tricky about this second graph is that the key on this side, the axis on this side goes up by 2s, and up here it goes up by 0.2s. I know that you can count it, but don't let it trip you up. So this is what your second graph should look like. We're starting to think about maybe seeing some patterns. Once you're done plotting your dots, don't forget to connect them. Okay, let's move on to graph number 3, ionization energy versus atomic number. Again, we're going to be utilizing elements 3 through 20 to create a graph of the atomic number on the x-axis versus the ionization energy on the y-axis. We're going to connect our data points with a straight line, and we're going to draw vertical dots separating different periods on our graph, just like we did last time. This time, I'm plotting atomic number versus ionization energy, which is the last number. So if we're doing for lithium again, we go to 3 for an atomic number, but our ionization energy is 124. So right here below 125. For our next element, we have atomic number 4, and our ionization is 215 for beryllium. So I'm going to go over on the x-axis to 4 and up to 215. And I'm going to continue plotting my points on my graph. Okay, and that's what graph number 3 should look like when you're done. And last off, graph number 4, we're plotting again in group 1 versus group 2, except for this time we're plotting the atomic number again versus the ionization energy. So go ahead and make a color key for what you would like to use for each one of these. For group 1 this time I'm going to do this kind of pinkish. Ooh, let's see, I'll do blue for group number 2. I'm just going to remind myself, kind of give myself a star. As I'm working through my key, I'm doing blue for group 2, pink for group 1. Okay, so that completes the graphing section. I'm going to let you analyze these trends when you complete the last section of this assignment by completing these questions. But first, I would like to move on to the one portion that we haven't gone over yet, which is, I know this didn't print really well in your at-home packets, but going over how do you draw these atoms by their atomic size in this periodic table. So, you're going to use the atomic radius listed for each element to draw to scale the size of each atom in the blank table. In order to do this, you're going to use the number listed for the element's atomic radius as the diameter in centimeters of your atom in the table on the back. For example, strontium has an atomic radius of 1.91, so the circle that you draw on the back will have a diameter of 1.91 centimeters. So if you don't have a ruler, do your best at home for estimating. I usually feel like a centimeter is about the length of the tip of my finger, so you can always use that for an estimation purposes. But just to kind of show you an example, we're just looking at where each element is here on this periodic table, and we're drawing it based off of what I've circled here in purple, which is the atomic radius. So if I'm working and I want to do lithium right here, which is in group 1, period 2, I'm trying to draw the atomic radius of this in terms of its size. So if its atomic radius is 1.23, I'm going to do that in terms of centimeters. So I'm going to start the edge of my circle, and I just want to mark the diameter, which is the length across the entire center of the circle. So I have 1, and then 0.23 right here should be about the diameter, and I'm just going to do my best job to draw this in a circle. And I kind of went over it a few times. If it's not a perfect circle, if it ends up as an oval, you're okay. So you can watch me go through these examples real quick, and it'll show you how you're supposed to build these atomic sizes. Just a quick note, with the ones that are listed here, we're splitting the transition metals right here. So you'll notice if you looked at a periodic table, we go from beryllium straight to boron. So you're able to skip the transition metals in the middle. Okay, and since this information is not available to you on your chart, you do not have to fill in these elements when drawing their atomic radius. The information you already have should be enough to complete an analysis of what these trends look like. Next steps are going to be to go to Schoology to complete this assignment. So if you're on our main Schoology page and you go into the folder on bonding, you'll see that we have a periodic trends activity. You can complete this activity either via Google Documents, as I'm going to show you right now. You can also complete it via a Word document that you would download and email to me. So let's see this document here. You open it up. There's some instructions, and you click here for the Google document, and this pops up. Obviously, when you have your own copy, you want to come up here and put in your own first name and last name. You've already made all these pictures, and you're going to insert your graphs here. You need the atomic radius and atomic number page, the ionization energy graphs, and then your drawings of your atomic radius. Once you've inserted those pictures, you need to answer these analysis questions in your own words and in complete sentences. You can go ahead and type your answers directly into this Google document. They should be really short-winded answers, no need for long paragraphs. Then when you're done, there's instructions on how to submit. As per always, if you have any problems with the submission, please just email me, and I'm happy to help you with your submission for this assignment. All right, everybody, that's all I have for you today. I understand that this activity is a little bit longer. It is worth more points in this category. I expect for the second half of class today, you are working on this activity. You should have a little bit of extra time on the next class time I see you if you need to finish this up. There's also office hours times from 1:30 to 3 every day, and you have until the end of the day on Friday to complete this. I'm available for any questions, and I feel like you have plenty of time to work through this activity. So just let me know if you need anything, and I'm here for you. Happy Monday!